Let's see, in terms of talks that are coming up, next month we have Michelle talking with us. And I'm sure you all know Michelle Toller. If you ever watch the Science Channel, how the universe works, and if you ever watch the launches like the Webb launch, Michelle Toller was the Goddard person that covered the TV coverage for that. Anyway, Michelle Toller is a great speaker, and she's an astrophysicist. She can talk about an awful lot of different subjects. And the question was, what should we have her talk about? I mean, she can talk about Webb, but I'm trying to get John Mather to come talk about Webb, but not sure I'm going to get him. Anyway, Michelle could talk about black holes, origin of the universe. Any particular subject you would like to hear about?
Origin of the universe.
I'm sorry?
Origin of the universe.
Origin of the universe. Okay. Sounds good to me. It's going to be between that and Webb. So that's the May luncheon. In June, I'm hoping Jim Garvin will come and tell us about either his Venus mission, that's in preparation now, the Da Vinci probe, I believe it's called, or I'm hoping he'll come talk about the Tonga eruption, volcanic eruption. It turns out Jim is still back in geology and actively publishing and doing research. And he had, in fact, published a paper of the Tonga region prior to the eruption. Now, this was a spectacular eruption, different than because it was underwater. There are lots of underwater eruptions, but most of them are effusive. They don't explode. This one exploded. So it produced an entirely different kind of cloud. Very little sulfur dioxide. There should have been a lot of sulfur dioxide. We don't know what happened to it, but we suspect it all got converted to sulfate really early during the origin of the eruption. So anyway, that's the plan for June. Now, normally we have the center director come in July, but unfortunately we can't get Dennis Andrusik schedule free enough, so he's not able to come. So we're working on speakers for July and August, etc. So that's the situation on upcoming speakers. If you have ideas who you'd like to hear, please let me know, and we'll try to work them in. All right, today we're fortunate to have Paul Mahaffy, who is just a new retiree. He just retired in December. He was the director of the Solar System Exploration Division. And in his background, he actually grew up in Eritrea, came to Canada and the U.S., got his PhD from Iowa State, and then after a short period of time, he ended up working in Hasso Neiman's branch, his atmospheric experiment branch. But now Paul has moved well beyond that. He's got the most awesome career. I mean, this is a dream career for an explorer. He's the PI of the Sample Analysis at Mars Instrument. That's on the Curiosity rover. It was launched in 2012, or arrived at Mars in 2012. He's also the PI of the neutral gas and iron mass spectrometer on the MAVEN Mars orbiter, measuring the composition of the Mars atmosphere. In addition to that, he's also was the PI of the neutral mass spectrometer on the LIDAR mission in the lunar orbit. That was launched in 2013, actually out of Wallops Island. And finally, he had a mass spectrometer on the Galileo probe of Jupiter. So, you know, Paul has been recognized with a whole bunch of awards. I just mentioned the 2014 John Lindsay Memorial Award and the 2013 American Chemical Society Maryland Chemist of the Year. So, Paul is going to talk to us today, bring us up to date on exploration of planets, moons, and primitive bodies.
Great. Thanks for the nice introduction. So I'm going to scan through a little bit of Goddard's history with planetary exploration, moons, planets, and primitive bodies. As I mentioned, I started actually along with John Haberman over there in the end of 1979. The group was just getting the Galileo probe mass spectrometer going. It was kind of the prime instrument on the Galileo probe to Jupiter. And there's an artist's conception of it parachuting into the atmosphere. Hasso Niemann was the PI on that. And it has some difficulties, of course, with the Challenger disaster. It didn't launch from the shuttle until 1989. Got to Jupiter December 7, 1995. And took 1 hour of data, worked beautifully as it parachuted down into the atmosphere. Probe data sent to a tape recorder of all things on the orbiter. And John will remember that it was kind of near solar conjunction, and so the first set of playbacks had all sorts of errors in them, and they played it back again, and we got the data down very successfully. So sometimes these planetary experiments take a while. I was in there turning knobs in 1980, along with John and Hasso Niemann, and 25 years later, we were publishing the data from trying to understand the formation of Jupiter and what the composition is trying to tell us. And in fact, this is just a beautiful mass spectra from 20 bar in Jupiter's atmosphere just before the probe failed. And these are mass to charge ratio and all the species and isotopes that we discovered in the Jovian atmosphere. It actually motivated another mission because the scientists were all expecting the atmosphere of Jupiter in the altitude that we were sampling to be very well mixed. So this was going to be the composition. But as we descended and descended, things like hydrogen sulfide and water just kept increasing, and we never got to kind of the well-mixed abundance. And so that motivated, even though we discovered a lot of things, that motivated the Juno mission, which now tries to sample very, very deep into the atmosphere and try to understand why the atmosphere is not homogeneous. So, as you all know, the basic goals of solar system exploration: how did our solar system form and evolve? And then a real driver, especially in the last 25 years or so, is there life elsewhere in or outside of our solar system? And then what are the different processes and environments in our solar system? So those are the motivating factors, and this is kind of the fleet of dozens of planetary missions. I've gone to every planet in the solar system and many moons, with a big focus both on the moon and Mars. Look at the kind of fleet of spacecraft at Mars, high-resolution imaging, high-resolution spectroscopy. Started off with Spirit and Opportunity landers and Curiosity rover, InSight trying to look at earthquakes on Mars and so on. So just a tremendous emphasis on Mars science for a reason that I'll talk about a little bit later. So the way missions are selected, just like in Earth science and heliophysics and so on, the big flagship missions are typically assigned to a center. In Earth science is typically Goddard and James Webb and so on, astrophysics, James Webb. And with planetary, JPL primarily runs those, but we have the opportunity to propose investigations, propose instruments. And I suppose several of you are probably pretty familiar with Cassini and Sears, which was a Goddard Infra-red Spectrometer, and Hasselino's gas chromatograph and spectrometer on the Huygens probe, and so on. But then smaller missions of a class lower than a flagship are Discovery and New Frontier. New Frontier is about $1 billion mission, and there it's all under the direction of a single PI. And they're selected targets that the decadal study defines. There are eight such targets now. And Discovery, a PI can propose going anywhere consistent with the goals of exploration that the decadal defines. And every 10 years, as in the other disciplines, earth science and heliophysics and so on, astrophysics, there's the National Academy of Sciences sponsors a decadal study. The last one was Vision and Voyages. And actually on the 19th, the results of the latest planetary decadal study are going to be out. We had quite a few people from my division at Goddard participating, so I got a few rumors of what was going on, but it would still be interesting to see what the targets are. The last decadal, I participated in the Mars panel, and the big impetus there, the big recommendation, which moved to the top of the list, was go to Mars and get a sample and return it to Earth. That had been studied for decades and decades, and now that is actually a program. So, again, the basic drivers: are we alone in the universe, and where and how do we search for life? And of course, it's been amazing ever since Galileo in 1610 made himself a telescope, put it together, and discovered the 4 moons of Jupiter. It's been just amazing being at Goddard 410 years after that. The Hubble was finalizing, the James Webb Space Telescope was finalizing assembly in the clean room in Building 29, and the progression of observational tools since then is just amazing. And now, of course, it's out in space. Everything's looking great, and this summer expect to hear all sorts of spectacular images from James Webb. So the particular areas of instrument expertise that Goddard's have, and I'm sure several of you are familiar with some of these, are these 4 areas. LIDAR, for example, MOLA, motivated by Jim Amshire and Jack Buffton and Jim Garvin, basically mapped out the topography of Mars, the lows being blue here and the reds being the mountains of Mars. You see Valles Marineris and Hellas Basin there. And with that expertise, Goddard's moved along to mapping Mercury, mapping the moon, and mapping the biggest asteroids in the solar system. That's in the series. Magnetometry has been a real area of expertise. Mario Kono basically sent dozens of magnetometers into space wherever he could. He was kind of the leader in that field before he passed away. And most recently, this is Jack Cannerdy's map of the magnetic field lines of Jupiter from the Juno orbiter. He's deputy mission PI on that mission, and just spectacular. And we'll move on to higher spectroscopy, but of course we can't get past Jupiter without, this is the Juno cam, and that's an outreach camera, and basically they turn the data over to whoever wants to play with it and do all sorts of stretching of the images. And of course, with all these amazing atmospheric features, you get these just beautiful, spectacular views of Jupiter. Higher spectroscopy, we finally, after decades, got to Pluto, and the infrared spectrometer developed at Goddard basically imaged the composition of the ices on the surface of Pluto, and that image was taken in 2015. Dennis Reuter and Amy Simon are kind of the science leads there, along with a lot of Goddard folks working on that. And then mass spectrometry. I won't talk a lot about this mission, but this is an ongoing mission. MAVEN, Goddard led. And although mass spectrometers measure composition of ions and neutrals, we've done some creative things. Here our mass spectrometer is hanging on this boom, this articulated platform, and the boom can articulate, and so we've done that as we're orbiting Mars, and that basically lets us find the direction that the horizontal winds on Mars are going. So we're mapping out the upper atmosphere winds. It was one of these opportunistic sciences. Okay, we're an extended mission. Let's measure winds on Mars. And so Lockheed Martin developed this capability to move the mass spectrometer point direction around. And we're very successfully, for the first time, measuring winds in the upper atmosphere of Mars. It's really interesting because as you go over, for example, Hellas Basin, you might imagine it's a very deep basin with temperature gradients, and even down low, the circulation is kind of pulling part of the atmosphere into the basin at certain times of the day, and that gets reflected all the way up to the orbit. Really interesting experiment.
So you're not measuring winds at the surface, you're measuring
right.
at orbit altitude?
That's right. We're measuring them right along the trajectory of the orbit. We can only do that. We're kind of elliptical orbit, of course. We can do that at the lower points of the orbit, and we've been doing that for several years now. So what I'm going to do is talk briefly about two current missions in operation. OSIRIS-Rex has really been exciting. It's a mouthful of an acronym: Origin, Spectral Interpretation, Resource Identification, and Security. But it's been hopping. Goddard's had a lot of involvement with that. It's a Goddard-led mission. December of 2018, we arrived at this asteroid Bennu, and of course you'll notice that there's kind of a theme of birds here. Bennu is an ancient Egyptian deity linked with the sun and so on. There's an image of that. And finally, after looking at the asteroid, getting into orbit, and figuring out a ample site, on October 20 of 2020, we collected sample. Just amazing, amazingly successful acquisition of a sample to return to Earth. So 2023, on my birthday, September 24, 2023, they'll parachute that sample down into the desert of Utah, pick it up, and we'll shortly have samples back in our labs on Earth. And so, of course, there are lots of asteroids that are identified, 500,000. There are about 7,000 near Earth, a couple hundred with orbits that you could, that are favorable for sample return. You want a small enough asteroid, there are 26 of them. And then you want a carbon-rich asteroid to understand all the complexities of what was going on in the early solar system with organic chemistry and so on. You know, these are kind of the seeds of chemistry that might have seeded the Earth and eventually resulted in life on Earth and so on. And so there were 5 of those, and then we got the prize on that one. And so, again, the infrared spectrometer during the orbital phase identified that there were hydrous minerals on Bennu that makes it really interesting. There are clays and so on. So these samples will be really interesting. And Bennu is just very, very rocky. So it was really tricky trying to find a spot to collect the sample. And you can see the rocks here. But there's then a lot of them kind of are porous and created spaces where you might sample. And so the team identified basically a number of sites that they might sample from, and in the end, the site, they named them all after birds, along with the theme of the mission. And Nightingale was the one that was selected. And the reason it was selected was, you can see, it's kind of not as rocky as some of the other places, and so that was a target. And you can see there's the target ellipse there. And these aren't real, these are SUVs on the surface of Bennu for scale, but you can see where the sampling target was. And so here's a camera on the Bennu spacecraft, on the OSIRIS-Rex spacecraft, coming down, basically slamming that tag system onto the surface and then backing off and basically releasing a gas from a nitrogen tank, which all drove material from the surface into this, what looks like an air filter. And so that was exciting. October 2020, and here they're closing the door there, and you can see all sorts of particles flying out, giving them good confidence that they really had collected a lot of sample, and putting it in the container for return to Earth, and it's now on its way to return to Earth. You can, if you've got good eyesight, you can kind of see that the sampling actually moves some of these rocks around. Here's a rock right in the middle, and it got moved over to this area and so on. So it was a pretty interesting event, basically, getting that sample off the surface. And then May 10, 2021, we said goodbye, OSIRIS-Rex, and headed back to Earth. And there'll be just an amazing amount of science coming out of that mission.
Do that.
On my birthday, September 24, 2023. And of course, they'll take the sample by helicopter over to Johnson Curation Facility, and it won't be too many weeks or months after that that we have a lot of analytic capabilities at Goddard. We'll be analyzing some of the sample. And just like Apollo samples, they'll keep some of the sample for future instruments that aren't even developed, but basically hundreds of scientists will be analyzing the sample.
How close is Bennu to Earth when they landed?
It's between Earth and Mars, and so yeah, it's not too far out. It's one reason, and it's in an elliptical orbit again, so selected the time that was favorable for an encounter. So near and dear to my heart is the Curiosity rover, because we had a big investigation on that. Basically launched in 2012, going to Gale Crater, this ancient lake bed. And there's the rover. There are 10 instruments on there. And huge credit to the expertise at Goddard. Our SAM experiment is to look for organics and to measure volatiles. And it's in the interior of the rover. Basically, the arm drills the sample and then goes above. We open some doors, we drop the sample in, and we analyze it. A mineralogy experiment is right next to us, ChemIn, to measure the definitive composition of the minerals, and then something like 28 cameras on the rover and so on, and many other experiments. SAM is actually it's just a credit to all the expertise at Goddard, is the most complex experiment that has ever landed on another planetary surface, at least as far as we know in our own solar system, but just numerous valves and plumbing and turbomolecular pumps, and all of that packed into this little box about the size of a microwave oven. And there's Bob Arby, who since passed away, basically spending about a year in the clean room assembling this, keeping it really, really clean. And then finally, in January 2011, we took it out to, actually we drove it out to JPL with a big truck and a small truck following it to keep them awake, and flipped the rover upside down and very carefully lowered SAM into the rover. They call this upside down position the dead bug position. So we put SAM in the rover and launched in 2011 on an Atlas. And you can tell by all the chairs at JPL in the control room, they're all very happy. This is just after touchdown. There's John Ratzinger and Charles Ilachi, the JPL directors there, and so on. And so very shortly after that, I was up in the control room, and through the dust cover, this is one of the HazCam cameras, and you can see Mount Sharp in the distance. You can see the shadow of the rover there. And it's just amazing seeing those postage stamp images come down from Mars. And this guy, Obama, was on Air Force One, so he called the team up and congratulated us. And that book, named the Mohawk guy, who was one of the mission operators, and so he cut his haircut. And so he turned into a real outreach person for the mission as well. And then this is our team. Actually, great diversity on this team. Florence Tan, some of you may know, was born in Malaysia. Bennu was born in Tunisia. And there's Chris Webster, who has the experiment with us in SAM, is from the UK. And Laurie Leshen is now the new director of JPL as of a few weeks ago. She's been off doing university president stints, and so it'll be good to establish a collaboration with her. So we're all happy it landed. We spent the first 3 months of the mission in this building at JPL, building 321, working on the Mars time. Of course, Mars time and Earth times are not the same. There's a 40-minute difference, so our clocks would change as the week went along. We'd be sleeping during the middle of the day, and we'd be having science team meetings at 3 a.m. or whenever we needed in order to get our next set of commands back up to the rover. And this is one of the very first images from the camera on the arm, which is a microscope, but it also has an infinite field of view. And so the arm rose up, and here it's pointing at the cameras on the mast, and the stereo cameras on the mast, and this is really just a fabulous image. So here's Gale Crater. It's 150 kilometers, formed by a big impact way back when. There's a central mound there, and of course we selected a site where there weren't too many rocks, where we thought we'd have a safe landing. And Gale Crater, so here's the history of the solar system, and you can't read the legends there, but from the cratering record, Gale Crater was formed sometime around there, sometime in a period that's at the end of the Noachian and early into the Hesperian, maybe 3.5 billion years ago. And that's kind of cool because that's about the same time that microbial life was developing on Earth. And so, of course, one big long-term question is, did life ever emerge on Mars? So here are some of the elements of SAM, our 74 sample cups, our mass spectrometer, our gas chromatograph from our French collaborators, tunable laser spectrometer from JPL, all packed inside our box and all inserted in front of the rover. Honeybee Robotics helped us build this sampling carousel system where we basically deposit a sample in a cup, we move the cup into an oven, and then in a helium flow, we look at the gases that are coming off of the sample. And so this is the type of data that the gas chromatograph mass spectrometer gets. We first heat up the sample and some of the gases come off. We collect a portion of the sample and send them to the gas chromatograph, and then that separates out organic compounds in time. So it's a really complicated lab-like experiment, and getting that to work on Mars, just a huge credit to the really rigorous engineering and testing that Goddard was able to support for this mission. So we landed here at Bradbury Landing. You can kind of see the scours from the descent thrusters exposing this. And each of those dots there is a new sol, a new day on Mars. And we headed not off in the direction of the hill where we were intending to go, but toward this unit that we saw off in the distance. Basically was 3 geological units, a cratering unit and a fractured LIDAR unit. And we thought that would be interesting to explore, so we did. And then right away we started understanding that, of course, from orbital observations, it looked like this might be an ancient lake might have formed here. But down on the surface, we could tell for sure. I mean, these sediments, basically, these layers, this cross-bedding is basically showing us that this indeed is representing the motion of dirt being moved around by water. And whereas Mars is red, the first drill hole that we drilled in February 2013 showed that underneath that kind of red surface, it's really gray, and it's really a clay. And clays are really interesting because they're potentially can retain and preserve organic compounds, which we're very interested in. And we could tell from this evolved gas curve in the mass spectrometer that this was a clay because that high temperature water evolution is from the dehydroxylation of the clays. And we also, here's the oxygen coming off, carbon dioxide, sulfur dioxide, and so on. So right away, after the very first few weeks, we concluded that a lot of the major, of course, you don't set your bar too high on mission objectives, but was Mars a habitable environment? And the answer was yes. I mean, there was water there in that lake for millions of years, and all the chemical elements, the ingredients for life, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur were there. And there were lots of minerals in various oxidation states that could have provided a source of energy for microbes, for example. And so just a wealth of information from the first samples. Those samples were so interesting that we didn't want to hang around that site forever. So we started doggy bagging some of the samples in our cup, drop them off in the cup, and then analyze them later. We actually have one sample still, after 10 years, that we haven't analyzed yet from Cumberland, the second drill hole that we drilled. And so here we are, here's where we landed, and almost 10 years later, we've gone almost 40 kilometers, and we're traversing up the mountain. We're now approaching this sulfate unit, which is probably representing a global change in Mars, a global change in the climate. So we're interested in seeing what this experiment can tell us about the ancient history of Mars. And here are just a few more of the drill holes that we've drilled. And this is kind of the type of data we get out from different gases that come off. So water, I talked about clays already. Sulfur dioxide comes from decomposition of sulfates and sulfides. We found that there were a lot of perchlorates in the sample that release both hydrochloric acid and oxygen when we heat them up, which is really interesting for future human exploration. That's something that folks will have to worry about. And then I'll talk a little bit about noble gas experiments, which provide some really interesting data. And then carbon comes either from organics, from combustion of organics, and so on. And there are various chlorinated carbon species. So again, these deposits here, these layering basically suggests that there was kind of a big lake there. It lasted for millions of years probably. There were rivers flowing into the lake. They deposited sediments, and the sediments show up in these layers in the rocks. And then at the bottom of the lake, there are lake bed sediments, basically material depositing down in the bottom of the lake. And then even after the lake dried out, there was subsurface water coming up, and as it flowed into the crater, it left deposits, primarily calcium sulfate, but you can see those all over the place. So really interesting experiment we'd never proposed, although we thought about it because we wanted to do it, was basically how to do chronology on Mars. Two types of chronology. One is as cosmic radiation, which blasts through the atmosphere. On Earth, we're largely protected by the atmosphere. On Mars, with 10 millibar pressure, radiation gets right down to the surface. And so there are various processes to produce noble gases. Nuclear spallation produces helium from a variety of elements, helium-3. Neon-21 comes from other elements. Argon-36 comes from other elements. And then there's some neutron capture processes that also produce argon-36 and potassium-84. And so if you could measure all those isotopes, you can get an age on how long that little bit of surface that you sampled has been exposed to this cosmic radiation. And that's really important because if there was ever life on Mars and you wanted to find DNA or something from a microbe, you would want it to be preserved so that radiation kind of blasts it apart. And so we measured these gases, helium-3, neon-21, and argon-36. And it's really satisfying to have 3 independent measurements of an age that all agree with each other. And so they were within air bars about 80 million years. And so that sample had been exposed, even though the crater was formed billions of years ago, the surface had been eroding away with dust and the wind. And that little piece of sample had been exposed for 80 million years, which is still a lot of radiation. If you had a cell there, E. coli or something, it would probably pretty well blast it apart. So that was a really interesting result. And then one other result from measuring noble gases, measuring argon-40, basically is determining the age at which that rock formed. And the reason you can do that is if you have potassium-40 in a sample, it decays with a really precise clock to argon-40 with a time constant, a half-life of 1.2 billion years of all things. And so we measured the argon-40, and then an elemental analysis experiment measured the potassium. And so from that, we concluded that the rock that we sampled on the second drill hole formed 4.2 billion years ago. And that's really an interesting number. And it's a good number because, you know, Mars only formed 4.6 or 7 billion years ago, so we got a reality check there. But it's also consistent with the cratering record, kind of near the top of the crater here. You can date that to about the same age, and some of those rocks that were formed from volcanic activity originally and then cratered away, made their way down into the bottom of the crater, and so it was a pretty consistent result. So that was really the first ever chronology experiment on another planet. And then we were looking for organics. We found a lot of them. Chlorinated compounds here. Chlorobenzene was kind of our first report, and chlorinated methane compounds. We found sulfur-containing compounds, thiophene, and so on. And so after this got published in Science, kind of the perspective write-up by Inga Kenkata was the detection of organic molecules, and methane on Mars has far-ranging implications in light of potential for past life on Mars. Curiosity has shown that Gale was habitable around 3.5 billion years ago, with conditions comparable to those on early Earth, where life evolved around that time. And the question of whether life may have originated or existed on Mars is a lot more opportune now that we know that we can detect organic molecules on the surface. But what about the atmosphere? Methane, of course, is really interesting because on Earth, most of the methane, 90 to 95%, is from biology. It's from rice paddies, it's from cow guts, it's from wetlands and landfills and so on. Basically, microbial life basically working on this organic matter and producing methane in the atmosphere, which is 1750 parts per billion on Earth. And we originally, first science paper, we don't see any methane, we got a null result. And then a few weeks later, it popped up. We saw methane as we ingested gas into the tunable laser spectrometer. And so what we think is going on is there are various seeps of methane coming out of the surface. And it looks like they're a little bit seasonal. As the surface warms up, you get a little bit more coming into the atmosphere. And it could come from either past life microbes that were existing way back when, and then the methane eventually makes its way to the surface. There are kind of also water-rock reactions that can also produce methane that are abiotic. So we don't have a definitive answer just by measuring the methane in the atmosphere. But what is really interesting is that we recently published 3 or 4 weeks ago, and you can't read this very well, but as we heated up samples, we kept analyzing the methane that we sent over to the tunable laser spectrometer, which measures methane with exquisite sensitivity. And the carbon isotopes in methane in the Earth's atmosphere are very diagnostic of microbial activity, because life likes to be efficient, and so those microbes, those methanogens that produce methane, they work harder on the carbon-12 than they do on the carbon-13, and so the products are depleted in the carbon-13. And so of all the samples that we looked at, there was one geological site where we had about 9 samples from, and they were very highly depleted in carbon-13. And so that's just fascinating. You know, you don't want to go out on a limb and say, well, you know, on Earth, that would be a dead ringer for life, so it is on Mars. So we also thought of, you know, potential abiotic processes that might have also created that light methane. But really interesting. I think it's one step toward, you know, if there's other evidence, it'll be one step toward a consistent story that way back when there was life on Mars. So we were so excited about it, we called up Thomas Brucken and gave him a briefing. And of course, the type of evidence that we would like are some of the more complicated organic molecules that are evidence of life on Earth. And so we're we're still looking for those, and future missions, of course, sample return and so on, will be able to do a better job if we get samples back on Earth. Now, I talked about that radiation destroying evidence of life, and so a mission we had been working on with the European Space Agency is ExoMars, where we were going to drill down 2 meters and get below that radiation dosage level and see if we could find complex organics. And to get a different type of mass spectrometer, we had a laser desorption mass spectrometer and also gas chromatograph and so on. Unfortunately, a few weeks ago, that came to a screeching halt because this was a collaboration with Roscosmos, and we were going to use their rocket to launch the spacecraft. And we've been working on this thing for 20 years now, and we've delivered the instrument to ESA. And so right now it's all on hold due to the disastrous war in Ukraine. But the one moral of the story is that on Earth, the evidence of ancient life kind of gets buried over time with geological processes, with plate tectonics and subduction and this and that. On Mars, much of the surface is very, very, very old because Mars dried out faster than Earth. And so there are environments where if there was life on Mars, we might be able to go there and take a good look. So I'm just going to mention briefly 2 other missions that Goddard won. Lucy is headed out toward Jupiter now. I went to the launch a couple weeks ago, and basically in the gravitational wells of Jupiter are captured what are called Trojan asteroids. Basically, asteroids were flying around the solar system early on, and Jupiter has such a gravitational well in these Lagrangian points that asteroids can be captured. And so this mission is headed out there basically to fly by a number of asteroids and take a look at them. And here are the artist's conception of they don't know exactly what the asteroids look like, but these are sized correctly, and see what they look like spectroscopically as we fly by them. And here they're assembling the infrared imager into the spacecraft. And of course, you've got to send up a time capsule. So there's a time capsule with lots of quotes from Yoko Ono, the Beatles, and Paul McCartney, and Sagan, and so on. And so as part of the outreach, kids are interested to encourage to form their own time capsule, and basically at some point in the mission, like when you fly by an asteroid and open it up and see what you're doing, 2030s, they'll be going by these various targets. And so that's part of the public outreach. And if you can get Jim Garvin or one of his deputy scientists to come talk to you, he just won a mission called Da Vinci, basically getting ready to go back to Venus. We've not been to Venus for a very, very, very long time. We've kind of mapped the surface in the late 80s with the Magellan spacecraft. And now, as part of the Discovery program, we have 2 missions going to Venus. One to parachute into the atmosphere and make measurements on the way down. That's Jim Garvin's mission. And the JPL mission, which will basically try and do improved radar mapping of the surface. And then really interesting, a couple of years ago, APL was selected to go back to Titan, which is a moon that has a real substantial atmosphere, with a quadcopter. And so here there's Titan. Of course, the surface is largely obscured except for a few infrared windows, but it's really cold on the surface. There are methane lakes on the surface. And so this will start. Parachute into the atmosphere is a pretty general parachute event because the atmosphere is so thick, but the rotorcraft will get its rotors spinning on the way down and hopefully land safely in 2034, and then make measurements on the surface, and then pick up the rotorcraft, go back into space, and find another site to analyze. So that's kind of a bit of a glimpse of what we've been doing at Goddard over the last little bit.
Very impressive.
Yeah, recent measurements of methane on Mars, did any corroborate what Mike MOLA saw 3 decades ago?
That's been always very controversial. And essentially, they probably, they've backed off the robustness of those measurements a little bit with further analysis. And it's very tricky because you're going through the Earth's atmosphere, which has a lot of methane, so you have to look at the Doppler shifts and all that. The other really interesting thing, of course, is what should have settled it all, was the Europeans sent out this Mars Gas Trace Orbiter, which just has exquisite sensitivity because it does solar occultations, and they have not detected methane at all, really, really low abundances. So what we think is happening from the Curiosity team, we're standing our ground and we've detected these plumes of methane, and what we think is happening is we make most of our measurements at night, and if these seeps come out of the surface, basically during the night in Gale Crater, the suppressed boundary layer basically keeps them from getting mixed into the bulk atmosphere. And then when daybreak comes along, then the sun heats up, you get all this turbulence, and it goes into a methane-poor atmosphere. And so about a year ago, we said, okay, well, let's prove that. So we made a day-night measurement. We made a measurement at night, and we saw very, very trace levels, less than a part per billion of methane. And then a couple days later, we made a measurement during the daytime, and it had all gone away. So our belief is that the Trace Gas Orbiter can't see that, because the lowest it measures is 20-some kilometers above the surface. But this methane is kind of very gently seeping out of the surface, and it's somewhat seasonal or episodic, but at night it builds up a little bit, and then when things get mixed in the day, but nevertheless, if Gale Crater was not unique, it should be building up over time to the point where the Trace Gas Orbiter could see it. And the fact that they don't see it probably means that there's some other destruction mechanism for methane other than the standard models of photochemistry, which say on Mars it should have a lifetime of about 300 years. So maybe interactions with dust or something like that. So still a bit of an open question. We keep hoping the Trace Gas Orbiter will find some methane as well, so we keep finding it on the surface now. We've devised a special experiment where we basically suck out all the carbon dioxide in the air to enrich the methane in our tunable laser spectrometer. And we always, when we do that, see, except for the day measurements, see methane lower than 1 part per billion, except for a couple spikes which have come along. So it's still a controversy, but I think the parts of the MOLA team have backed off a little bit from their early remote sensing observations. Mike, I'll give you a different answer today.
Yeah, the sedimentary rocks we're looking at on Mars, I presume they were positive when the atmosphere was much thicker.
Right.
Yeah, what do we know about the atmosphere in those days?
Yeah. So that was one of the prime objectives of the MAVEN mission, from measurements made in orbit to try and understand how much of the atmosphere has escaped to space. On Earth, a lot of the carbon dioxide that was originally in the atmosphere, of course, reacted with water and precipitated out as carbonates. So you have the cliffs of Dover and everything, which are a signature of that. And on Mars, there are some carbonates, but not in enough abundance to really explain a lot. And so what's happened is a lot of the Mars atmosphere has escaped to space. And so the conclusion from the MAVEN team is that probably maybe several bar of atmosphere over time from way back then were lost to space. They don't have a precise number, but we're measuring ongoing loss rates and trying to extrapolate back. Of course, the sun has been changing in the meantime, so it's a fairly complicated extrapolation. But yeah, the atmosphere was probably much heavier back then.
Support the idea of liquid water.
Right. Yeah. Yeah.
Any other questions?
Thanks for your attention.